to talk about rotations and dilations. Most of this is going to be repetitive from what you've seen in the past, except for one concept with rotations that we're going to spend a little time on. So just to recall, a rotation is a transformation. It turns a figure around a fixed point. That's going to be called your center of rotation. It also preserves shape and size. So it's going to be an isometry, and the image of the rotated figure is congruent to the pre-image. So it's a congruence transformation, like we just spoke about yesterday. So your center of rotation, again, we can call it point P here. You guys can always assume that when we rotate, we're going to rotate counterclockwise. So the pre-image of A rotates to become A prime, and both of these are going to be equidistant from the center of rotation. So that's all it's telling us right here. Also, angle A prime P A is going to be the angle of rotation. So we're going to linger here for a few minutes. And we're going to get into, in your book it talks about a 90-degree rotation, a 180-degree. I'm also going to talk you guys through a 270 and a 360 just so you see it. But these are the two that you're primarily going to see in your book and in examples. So here, this is one thing I don't want you guys to do is memorize this. All right? This one is pretty obvious, it makes sense, but this one is flipped and negated. So I want to show y'all where that comes from. So you can always assume that your positive x-axis here is going to be your reference point. And like I told y'all, we're always going to be rotating counterclockwise. And as you guys know, each axis is going to be 90 degrees. Okay, so if I have the point 4, 2, and I rotate it 90 degrees, I'm going to end up at the point, according to my little formula, negative 2, 4. That's different than a reflection because, of course, if you reflected from across your y-axis, you'd be equidistant. So in this case, I would be negative 4, 2. To me, that's the point that you have to keep straight in your head. All right, so let's go ahead and let's think about it in terms of our axis. So in order to get to this point, I went 4 steps to the right on my reference axis, and then I went 2 steps up into that quadrant. So if I'm going to take this guy, and I'm going to rotate him over, I end up, according again to my formula, at negative 2, 4. So essentially, just as I went 4 into on my reference axis and 2 into the quadrant, now you can think about it like this. Now I'm going to go 4 on this reference axis and 2 into the quadrant, and that gets me to negative 2, 4. I can carry it on. So if I took this guy, I'm going to end up, according to this little formula here, I'm going to end up at negative 4, negative 2. Okay, well now I want to get into this quadrant if I want to go 90 more degrees. So I'm going to take 4 steps towards my endpoint, towards the quadrant I want to be in, on that axis, and then 2 steps down. And that gets me to negative 4, negative 2. And then if I wanted to take it to 270 degrees, I'm going to go 4 in and 2 to the right. So that's going to give me 2, negative 4. And again, if I wanted to take it back home to 360, I'm going to end up exactly where I started from. So the quadrant and the axis that you're stepping into is going to be your reference. So here, guys, this pretty much lays out exactly what I was talking about. Here's your 270, here's your 90, here's your 180, and here's your 360. If you guys do want to take a second and write down these little formulas, I think will be helpful. But again, if you just kind of follow those patterns in that step, that's going to get you where you need to be without having to memorize. So let's go through one of these examples here. We have negative 1, 3. This notation, you will not see this in your book, but this notation basically just says that this is what you're rotating, okay? I want you guys to pause the tape and take a second and just fill out this. These 2 guys in are what you're going to see in your book, but I think it's good for y'all to see these as well. So here are your answers, guys. This might be a good good notes quiz when I see you guys next. Alright guys, so now what we're going to do is we're going to just revisit dilations. A little bit of the notation is going to be a little different than y'all have seen. Again, you're not going to have to really worry about that in the book, but I think it's good for you guys to see it. See guys, a dilation is not going to be a congruence transformation because it does change the size of the figure. We're basically blowing it up or we're shrinking it. Now, the image and the pre-image are not congruent, but they are similar. We did a lot of that work in chapter 7. So they're going to have the same shape. The angles are going to be congruent. The sides are going to have the same similarity ratio. So let's kind of revisit that. So this is really the only new thing that you guys are going to see here. For a dilation of a scale factor of k, if k is bigger than 0, meaning k is positive, all right, remember k is your scale factor. The figure is turned but not flipped, okay? If k is less than 0, the figure is rotated by 180 degrees. And this is the thing that we're going to spend a little time on. The rest of it is repetitive. And just a little reminder, you guys, let's write this down. Your similarity ratio, for example, if it's 1/3, your scale factor is the reciprocal. So it's going to be 3/1 or 3, all right? And the order matters on where you're going. The other thing that we'll talk about here is going to be your center of dilation, just a little vocab. So if this is my center of dilation, these guys right here, if this is dilated, it grows. Then this distance over this distance is going to be the same. So basically that's where your similarity ratio is coming in. Okay? So your scale factor here is going to be this over this. Alright? Your similarity ratio is PQ over P prime Q prime. Just a little bit of a mathy way of saying what we've already said before. Then we also have our enlargement, just as a little reminder. If the scale factor is greater than 1, this is a good thing to keep in mind, it's going to be an enlargement. If the scale factor is between 0 and 1, it's going to be a reduction or contraction. You guys will hear me say reduction, but contraction makes sense. It's contracting to a smaller space. Okay, so again, this is something that you guys have seen before. We did a lot of work on that. Y'all did a great job with it. This is the same thing that we talked about with our similarity ratio and our scale factors and the relationship between them. Let's go through and let's look at one of these. This is the notation I was talking about. Guys, all this is telling me is that is dilation of triangle XTR to triangle X prime, T prime, R prime, and enlargement or reduction. Okay, and remember what I told y'all, your order is going to matter. Alright, so let's go ahead and let's check it out. This is just telling me that this is point X, you guys, which is the same as X prime, because my center of my center of dilation is going to be right here, so it's growing from that point. Alright, so let's look at this, guys. Remember, in order to figure out your similarity ratio, you're going in the order that it gives you. Okay, so what is our similarity ratio? 4 over, here's my big guy, careful guys, when I was first doing this I made this mistake, it's not 4 over 8, which is what it's trying to get me to do here, it's 4 over, what is this distance right here, 12, okay, so my similarity ratio is 4 over 12, which simplifies to 1/3, therefore my scale factor is going to be what? The reciprocal of that, it's going to be 3. Okay, because of the fact that I'm going from my black to my blue, you can obviously see it's an enlargement, so we can go ahead and get rid of these guys immediately, and we know that the answer is going to be B here. Okay, so again, this is a process we went through, we talked about it a lot, y'all did a great job with it, but just as a little friendly reminder. Alright, and again, don't get too hung up in this notation right here. The main thing is going from your triangle X star to X prime, T prime, R prime. Okay, and then of course it would be reversed if I went backwards. If I went from my primes from my blue to my black, then I would be shrinking it. Notice your scale factor is 3, so it's going to be an enlargement. It's bigger than 1. So just as a quick reminder, what are the coordinates of the vertices of triangle PZG with a scale factor of 0.5? So because I know that it's less than 1 but greater than 0, I know that it's going to be a reduction. And all I need to do is I need to multiply each of these by 1/2. So when I multiply each by 1/2, it gives me the new coordinates. You guys are fine to use a decimal or a fraction. Multiply each of these by 1/2, and I get 1 and negative 0.5. And multiply each of these by 1/2, and I get 0, and I get negative 1. So this is going to be these are going to be the new coordinates of my reduction here. All right, you guys, this is the last thing, and this is just a little bit different, just because it has the negatives, but the process is exactly the same. So this is what I talked about before. So if the scale factor for a dilation is negative, all right, this is something that we did not see. So you just have a negative k. You're going to do the same process. The pre-image is rotated by 180 degrees. So let's just check it out. And then I think when you see some actual examples and do some in your homework, it'll fall into place. So here's going to be my pre-image. If the scale factor is 2, let's say, all right, then this, of course, in fact, let's do this. Let's call A 0.11. Let's say we have a scale factor of 3. I used 3 in my notes here. So that means that 0.11, A prime, of course, is going to become 3, 3. Okay, here's your 3, 3 right here. All right? So now, because of the fact that the scale factor is negative 3, what happens is this guy goes down to this quadrant. So it's going to be negative 3, negative 3. That's the same pattern that we saw with the 180-degree rotation. Same coordinates, it's just negated. So what it's going to do is it's going to take that thing and rotate it 180 degrees. Again, it piggybacks on the rotation formulas that we just talked about a second ago. Your center of dilation is going to be your origin in this case. And so just as our last example here, so y'all can see it, it's going to tell us draw the image. I'm fine if you guys just want to put your ordered pairs down instead of drawing it. It might help you guys for some of this to draw this, so do it if you need to. And under the dilation with scale factor of -2. All right, so this is essentially going to be an enlargement that's rotated because of the fact that it's negative, but it's still, k is still bigger than 1. So here we go, guys. A prime, of course, I'm just multiplying -2 to both of these, and you get 2, -2. Not sure what it is I'm writing there. 2, -2. 4, +2. And 2, +4. Here's what your drawing looks like. And you guys can see that, again, it is rotated 180 degrees. In this case, it rotated it clockwise, but it's just because of where our original shape was oriented. And you can see how it enlarged it as well. All right, so that's all I got, you guys. We're going to do our homework in class on Wednesday. And I made a point, again, there's no need to draw these if you don't want to. You can just write the ordered pairs down, and I'm fine with that.